and it says PDE. Oh, by the way, there's a PDE button. PDE mode, show subdomains. I can actually, we're going to come back and do another example. We're going to go through this whole thing, and then we're going to start seeing how we can play around with domains some more. Okay? But you basically do all this. Oh, by the way, check this out. Export PDE coefficients. Like I said, you can export all the pieces of this that you want. Okay. Well, let's go ahead and push PDE. And what ends up happening when you push PDE, this comes up. PDE specification. Here's where the magic all sits, in some sense. If you look at this, there's basically here, it says here, equation, right? This first line says equation. It gives you the equation, which is a U. It's an equation for U, right there. And notice I have 4 little check boxes. I can solve an elliptic equation. I can solve a parabolic equation, a hyperbolic, and eigenmodes. Okay, so what are the differences? So let's look at this equation. It's two-dimensional. It's the divergence of C times grad U, where C is specified down here, plus AU equals F. Okay, so this is a generalized version of a Laplace's operator, right, with a spatially dependent term here. So this is like your second derivative. Hey, by the way, it's only going to second derivatives because it's actually going to use simplex methods for everything here. And it can't do anything more than 2 derivatives, right, with a simplex method. Because if you take 2 derivatives of that simplex, you know, it's one thing. Remember, we're going to write this in an integral formulation. So 2 derivatives become 1 derivative squared. So if you use a simplex, you can still get information. 3 derivatives, however, can't handle them. Even if you integrate it up once, you still have to take 2 derivatives, which will tell you nothing with the simplex. So this is like the spatial diffusion term plus AU equals F. There's no time in there anywhere, right? This is just spatial. And that's why it's an elliptic problem. You get to specify A, F, C. You can make very complicated functions. The default is C is 1, A is 0, F is 10, which is totally random. Why would you pick F as 10? They do. Fine. That's your default. But you can say, hey, look, A is not 0. It's cosine X. You know what? C, yeah, in fact, that kind of has spatial behavior, and it's, you know, I don't know, sine X plus Y. Ooh, look at that, fancy now. 2Y, whoa, even fancier. Okay, so you can just do whatever you want here. And my forcing is this. 10 is fine. Okay, we'll come back to that. So that's an elliptic problem I can impose. Let me just tell you what the difference are between elliptic, parabolic, hyperbolic, and eigenmodes. They're basically going to be all the same thing. They're going to be this equation here, the governing equation. And what elliptic is going to do is just going to say, add ut in front of this. U of t equals this. So all of a sudden this becomes like a diffusion term. Hyperbolic, UTT equals that. Now it's waves. Okay? So in other words, if C is constant, this becomes, in 1D, UT equals UXX, heat equation. It's parabolic. Or UTT equals UXX for the hyperbolic, which is waves that travel left and right. And then if you go to eigenmodes, it's equal to lambda u, where you know what the lambdas are. So it's an eigenvalue problem. Notice that they're all linear. Bummer. What do you have, a nonlinear problem? Well, PDE Toolbox isn't going to do anything for you. Okay? Nonlinear problems, I believe, in fact, some of the other toolboxes do handle certain forms of nonlinearity for specific applications. Okay? This is where they do not allow you to just pick your nonlinearity. Why is it linear, by the way? It's linear because, at the end of the day, what is it going to solve? X equal to B. Okay? And then you're like, oh, what happens if I have a nonlinear equation? How many solutions are there to a nonlinear equation? I have no idea. Could be 1, could be 0, could be 1013. Okay? And to get to the right one, you kind of have to guess the right one. Right? All the nonlinear solutions are iterative solutions, and they assume that you can guess closely to get the solution. Out of the 1013, you're looking for 567. Well, you better guess close to 567. And this isn't going to get into that with you. Okay? All linear. So let's look at the parabolic. Boom. Did I tell you? I told you. UT. U prime. See that U prime there? One derivative in time. And I can even put in a coefficient that depends upon x, y in there. Pretty sweet. And I can even make these parameters dependent upon time. Like I can come in here and say, oh yeah, by the way, times cosine t. Now that time's in there, fair game.
So is that true for all the coefficients and all the frames you can make the time variant? Like the boundary conditions, for example.
Yeah.
Can they be time variant?
Yeah.
But not a function of u. They can't.
But not a function of u, that's right. Then you'll get a complaint. Hyperbolic. 2 primes. I know you can barely see that. You can't even see that. Can anybody see that? And if you do, you got too good eyes. You got to be studying harder. You're not studying hard enough, you can read that without glasses. Okay? All right. And then eigenmodes. There's no f, there's just a lambda du. So pretty complicated eigenvalue problems you can solve. In fact, I could go back to this problem here. Let me go back. Let me close this for a minute. Oh, go back to elliptic. Take this off. Okay. I can go back to here and say, I just made this cool-looking drum. What does it sound like? I could come over there, and before I built this drum, right, I could go and I can actually calculate all its frequency components, right? I could calculate the eigenvalues of that drum shape. That's pretty cool. Maybe not that cool. But anyway, I could do that if I wanted to, right? But we've just specified the PDE. And that's the PDE we had. We left it here. We put in some terms. And we said, OK. All right.
Did you domain the interior of this?
The interior, yep.
It's not a funny-shaped wing, you know?
Not yet. Not yet. We'll get to the funny-shaped wing. All right, so look at this. We're just moving our way from left to right, just like you read. Just like you read. All right. Except if you're in China, if you're from China, then you have to go backwards. Okay, you have to start off on the end of the sentence, right? Then you guys, you read right to left, right? Chinese? Is that right? Some? Oh, anyway, I thought. Well, anyway, we're going left to right.